Hi, hello everyone. Hoping you're having a productive day today. Welcome to a new video in my YouTube channel specialized in IB programs, supporting hundreds of students from more than 30 countries. I have supported many students from over 30 countries in the past 4 years, IB students in both physics and mathematics. Today I'm going to discuss Coulomb's law, and I'm going to touch on electric permittivity, and let's see what is this, and some application on using the concept of Coulomb's law and electric permittivity. Okay, so let's keep going. So in 1785, the French scientist Charles-Augustin de Coulomb published the results of his series of experiments that to investigate the relationship between the electrostatic force between two charged objects, the amount of the charge, and the separation between them. So let's say we have a Q1 and Q2, two charged objects, right? It depends on the type of charges. You may see either a repulsive force or an attraction force. Obviously, if the charges are similar, they are both positive or both negative, you will experience a charge will experience on the other a repulsive force. If the charges are different, so then the force will be an attraction force. Okay, so for more detailed information about the apparatus or the device that Coulomb used, I'm going to share a link to a video in the description below. So if you are interested, you can get more information about the techniques of the experiment themselves. But from the perspective of a physical formula here, okay, so what we can say that F, the force, is proportional to the amount of charge, okay, or basically the product of Q1 times Q2, okay, and that is, let's say, equation 1 or relationship 1, and then the force will be inversely proportional to the square of the distance between the two charges, okay. So to combine these two relationships, we can say, okay, so F is proportional to Q1, Q2 divided by R squared. And then we can replace mathematically the proportionality symbol by equal sign, but then you need to multiply by a constant, which is the constant of proportionality, right? So this constant here is going to be K, and it is called Coulomb's constant. So F equals to Q1, K, Q1, Q2 over R squared. And this is the mathematical formula for Coulomb's law, where the force here is in Newton, Q is quantity of charge in Coulomb, and R distance between the charges or the point charges, and is in meter in SI system. In some textbooks, R, they call it the separation or the distance between the centers of the two charges, given they are spherical bodies. That is fine, but by definition, we usually use the concept of point charge. So point charge is a theoretical concept to make definitions easier in physics. Like we use point mass, for example, when we talk about gravitational law of Newton, right? So point charge is very, 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 very small. So that's why we say, okay, the distance between the two point charges. So the statement of Coulomb's law at the end of the day, the electrostatic force between two pointed charges is directly proportional to the product of the magnitude of the two charges and inversely proportional to the separation or the distance between them. Okay? Now let's talk a little bit about K, the Coulomb's constant. By the way, Coulomb himself did not find or discover the constant. It was actually done by Gauss and Maxwell, who did continue the work after Coulomb's results, and actually they, they proved, or they found the theoretical constant to be 8.99 times 10 to the power of 9, and it is in your data booklets. You don't have to memorize it. And if you would like to investigate or determine, the units of K, you look at the formula, rearrange. So K is going to be F times R squared over Q1 times Q2, right? So it's going to be Newton meter squared Coulomb minus 2. Okay. Now, very important remark, this value here is used only if the medium between the two charges is air or vacuum. Okay. Why is that? Because K actually has a relationship between the permittivity. So K is actually 1 over 4 pi epsilon naught. So epsilon here, this Greek letter is called epsilon. So epsilon naught here means the permittivity of the free space. The permittivity of the free space. And I'm going to talk about the permittivity in a few minutes, right? But what I want to say here, this is a permittivity of free space or vacuum. If you actually, it is, okay, is equal to 8.85 times 10 to the power of negative 12 Coulomb squared Newton minus 1 meters negative 2. So if you plug in this formula here, 1 over 4 pi epsilon naught, and you plug this number there, you will get this value here to 3 significant figures, 8.99, and this is the value we are using in the data booklet. But again, this is only in case if the medium is vacuum or air. There is a slight difference between air and vacuum, but for practical use, we are going to assume they are basically the same. Okay. The permittivity itself depends on the speed of light, and since the speed of light in air is about 0.03% slower than the speed of light in vacuum, so again, in other branches of physics, like wave physics, we take only one value for both air and vacuum for the speed of light, and we just round it to 3 times 10 to the power of 8 meter per second. So this is just a little bit of background on the permittivity. But now let's really define, let's really know, okay, what is this? Okay. So the electric permittivity, epsilon, is a measure of the resistance offered by the substance in creating an electric field within it and affects the transmission of the electric force. The SI unit of permittivity is farad or farad meter minus 1. Okay, so physics permittivity is like how easy for an electric field to pass through a certain medium. This is basically the permittivity, to permit electric field, that is created by the charged particles, right? Now this table here below represents some what we call the ratio epsilon r, the relative permittivity epsilon over epsilon naught. So epsilon r is called the relative permittivity. Okay, relative. So epsilon r is called relative permittivity, right? And by definition is going to be epsilon of the medium, of any medium, let's say paper, mica, over the epsilon naught where that is the permittivity of free space. Okay, so as you see here from the table, okay, for vacuum, of course, it is 1, but for air it is very close to 1, like 1.00054, due to the slight difference of the speed of light in air versus vacuum. But again, in terms of problems in physics for IB, we take the same value, you know, for both air and vacuum. Okay. So epsilon r is one way to give you an indication in the question that the medium is not air. Okay. So one option, if you see epsilon r, you need to use epsilon. So now I'm going to write down the general form of Coulomb's law. Okay, is going to be, instead of k, I cannot use k. I will just say 1 over 4 pi epsilon only, not epsilon naught, because here epsilon for any medium, right? Multiplied by q1 q2 over r squared. Okay, so in this case I need epsilon. If given epsilon r, so epsilon is going to be epsilon r multiplied by epsilon naught, obviously just simple cross multiplication, right? So if you are given in the problem epsilon r, you can just multiply it by epsilon naught, which is in your data booklet 8.85 times 10 to the power of negative 12 farad meter minus 1. Okay, the second option, you may be given epsilon right away. Okay, so for example, like I can give you epsilon for let's say graphite. Okay, so if the medium is graphite between the two charges, so obviously I'm not going to use epsilon naught anymore, so I have to use the value of epsilon graphite, and it could be given in the question around 106 times 10 to the power of negative 12 farad meter minus 1. Okay, now let me talk a little bit about farad, the unit. So farad actually it's on the high level on the HL side of the program. It doesn't hurt to talk a little bit about it. So farad actually is the unit of the capacitance of a capacitor. Okay, so the capacitance, I mean, lots of C's, you know, you have to be careful. Now C here is not Coulomb, it's just a capacitance, you know, it's a physical property of a capacitor, which is the quantity of charge that is stored on a plate of a capacitor per 1 volt, per unit potential difference. So it's basically Q over V. Okay, so if Q in Coulomb, V in volt, so capacitance is Coulomb volt minus 1, and we call this farad. SI system. Okay, now volt, we know from previous video when I talk about derived physical quantities in electric physics. So potential difference is basically work done over charge, or energy, electric potential energy divided by the charge per unit charge. Okay, so this is W over Q, right? So 1 volt technically is joule Coulomb minus 1, and joule is Newton meter. Joule is work done, force times distance or displacement, so Newton meter Coulomb minus 1. So this is volt. I can say this is volt, joules Coulomb minus 1, or Newton meter Coulomb minus 1. So back here, now let me just change the color here. So back, I want to see, okay, what is this farad meter minus 1? So this we have here farad, okay, meter minus 1. So farad itself is Coulomb volt minus 1. So you can say Coulomb volt minus 1 times meter minus 1. Now volt minus 1, okay, is basically the reciprocal of this, right? Because volt, as I mentioned, we can express it as joule Coulomb minus 1, right? Or Newton meter Coulomb minus 1, and even I can break it down more, but I want just to leave it as Newton for now. So we can say, okay, so this can be Coulomb. Now the reciprocal, so it's going to be Newton minus 1, meter minus 1, and then Coulomb, and then meter minus 1. So if you simplify this, that will be equivalent to Coulomb squared, right? Newton minus 1, and then meter negative 2, which is the units I wrote down here in the previous slide. Coulomb squared, Newton minus 1, meter minus 2. Again, I'll not memorize these units. I can prove it in 5 seconds. And this is important skills you need to develop with me during the program. Okay. So if you are high level, if you take physics high level, so that's fine. You learn that. If you are on the standard level, so you don't need to worry too much about the farad. You need to know how to apply the permittivity. Okay. So the bottom line, if the medium is air or vacuum, you're gonna use epsilon naught or K right away. If the medium is not air or vacuum, so you're gonna use epsilon R or epsilon of the medium itself. Now let's have a practice problem. This problem here from Cambridge textbook. Okay, so let's have a look. The electric permittivity of graphite is 12 times greater than that of vacuum. Okay, so this is a given. So we can say, okay, I can write the given here. So epsilon of graphite. So this is epsilon, electric permittivity, right, is equal to 12 times epsilon naught, because it says that of vacuum. Now, the force between 2 point charges in vacuum is F. So F is basically 1 over 4 pi epsilon naught, because it's say in vacuum, times Q1, Q2 over R squared. Now, the two charges are embedded in graphite, right? So now the permittivity will be different, and their separation is doubled. Predict the new force between the charges in terms of F. Okay, so let's call the new force F prime. So F prime is basically in graphite, right? So in this case, it's going to be 1 over 4 pi epsilon graphite multiplied by Q1, Q2. Now, R, and instead of R, I'm going to replace it by 2R, and be careful, we have a square, so it's 2R all to the power of 2, which will be 4. So be careful, when you double the separation, you double R only, but then don't forget to square it. Don't forget to square it. I have seen it a lot. So, okay. So, and now I can replace epsilon graphite by 12 epsilon naught, right? This is given. And then Q1, Q2 divided by now 4 R squared, 2 squared is 4. So that's easy. So now this is F prime of graphite, and we need to find in terms of F. You can divide F prime over F, right? Or we can see, I can here easily, I can rewrite this a little bit, you know, like I can bring 4 pi epsilon naught on the side here, Q1, Q2 over R squared, and then see what is left. So what is left, left down here, 12 times 4, right? So I can say, okay, so all of this part here is basically F. So this is kind of smart way, quick way. If not, you can always divide, you know, F prime by F. So this term here is F, right? And then we have at the denominator 12 times 4, which is 48. So the answer here is the force in graphite in this case, and with doubling the separation, is going to be 48 times less than the force in vacuum. Okay, so this is how you apply the electric permittivity if it is different than vacuum in certain questions. So I conclude my video. I hope it was helpful. Thanks for listening. Thanks very much for listening. And please leave any comments, likes, whatever you want, and see you in a further video. Have a nice day.